Section 8.2 Vectors in the Coordinate Plane. A vector OP in standard position on a rectangular coordinate system can be uniquely described by the coordinates of its terminal point. We denote OP on the coordinate plane by xy, and these are chevrons. Notice that x and y are the rectangular components of OP. For this reason, xy is called the component form of a vector, and when we use the chevrons, it means it's in component form. When a vector is in standard position, that means its initial side is on the origin. Since vectors with the same magnitude and direction are equivalent, many vectors can be represented by the same coordinates. For example, vectors p, t, v, and w in figure 8.2.2 are equivalent because each can be denoted as 3, 2. To find the component form of a vector that is not in standard position, you can use the coordinates of its initial and terminal points. So each of these vectors can be represented by 3, 2. All of their x components are 3, and all of their y components are 2. So it doesn't matter where the vector is. As long as it has the same length or magnitude and the same direction, they're equal. They're all the same. Component form of a vector. A component form of a vector AB with initial point A, x1, y1, and terminal point B, x2, y2 is considered by x2 minus x1, y2 minus y1. So in order to find out how far or what the x component is and what the y component is, you just subtract the x's or you subtract the y's. Express a vector in component form. Find the component form of AB with initial point -4, 2 and terminal point 3, -5. Now, in order to complete the problem, all you have to do is subtract the x's and subtract the y's. 3 minus -4 is 7, and -5 minus 2 is -7. Now that means we have this vector starting at -4, 2. 1, 2, 3, 4, 2, and ending at 3, -5. 1, 2, 3, 1, 2, 3, 4, 5. So we have this vector right there. And we can represent that vector in component form with the point 7, -7. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. In other words, this vector right here is the same as that vector right there. But the answer is just 7, -7. Magnitude of a vector in the coordinate plane. If v is a vector with point xy and terminal point x2, y2, then the magnitude of v is given by, this is just the Pythagorean theorem. If v has a component form of ab, then the magnitude of v is just the square root of a squared plus b squared. If the vector is in component form, we've already taken care of the subtraction. Now, any non-horizontal or non-vertical vector, we can find the length by just making a right triangle and doing the Pythagorean theorem. Find the magnitude of a vector. Find the magnitude of AB with initial point -4, 2 and terminal point 3, -5. So the magnitude of vector AB is going to be equal to the square root of, we have 3 minus -4, that's 7 squared, plus -5 minus 2 is -7 squared. That's equal to the square root of 49 plus 49, which is the square root of 98. Operations with vectors. Find each of the following for w, y, and z. W plus y. To add two vectors together, you just add the x components together, add the y components together. So this answer is -4 plus 2 is -2, 1 plus 5 is 6. With b, we have z minus 2y. Z is -3, 0. Then we have minus 2 times, y is 2, 5. 2, 5. And we can start out by multiplying, -3, 0. Minus 4, 10. -3 minus 4 is -7, and 0 minus 10 is -10. A vector that has a magnitude of 1 unit is called a unit vector. It is sometimes useful to describe a non-zero vector v as a scalar multiple of a unit vector u with the same direction as v. To find u, divide b by its magnitude v. Divide v by its magnitude. Find a unit vector with the same direction as a given vector. Find a unit vector u with the same direction as v, negative 2, 3. So the new vector is negative 2 divided by the magnitude, 3 divided by the magnitude of the vector. And the magnitude of the vector is the square root of 4 plus 9. That's negative 2 squared and 3 squared. That's the square root of 13. So negative 2 over square root of 13, 3 over square root of 13. And this vector has a magnitude of 1 and is in the same direction as negative 2, 3. The unit vectors in the direction of the positive x-axis and positive y-axis are denoted by I and j respectively. Vectors I and j are called standard unit vectors. So I has a length of 1 and it goes along the x-axis. J has a length of 1 or magnitude of 1 and it goes along the y-axis. These vectors can be used to express any vector v equals ab as ai plus bj, as shown in figure 824. If vector is AB, you could split that into A, 0 and 0, B. Then you could take the A out. That would be 1, 0 plus B times 0, 1. And then 1, 0 is the I and 0, 1 is the J. So you can write the vector as AI plus B times J. Let vector DE be the vector with the initial point negative 2, 3 and terminal point 4, 5. Write DE as a linear combination of the vectors I and j. Well, vector DE can be written as 4 minus negative 2 is 6, and 5 minus 3 is 2. Now we can write that same vector as 6i plus 2j. Find component form. Find the component form of the vector v with magnitude 10 and direction angle 120. Alright, so if we have this angle that's 120 degrees right here, and if this was the unit circle, the x-coordinate would be the cosine of 120, and the y would be the sine of 120. But we don't have a magnitude of 1 like we do on the unit circle. We have a magnitude of 10, so we just multiply the cosine and the sine times 10. So the component form is 10 cosine of 120 and then 10 sine of 120. Cosine of 120 is negative 1/2, so this is negative 5, and the sine of 120 is square root of 3 over 2, so this is 5 square root of 3. Example 7. Direction angles of vectors. Find the direction angle of each vector to the nearest tenth of a degree. If we have the vector 3i plus 7j, that can be written as 3, 7. And we could plot that point. We could find the position. We have 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. So we have 3, 7 right there. And that's the vector in standard position. We could draw a line to the x-axis. If that's the angle right there, this is the x, this is the y, and the x is 3, the y is 7, and we can say that the tangent of the angle that we're looking for is equal to opposite over adjacent, or sine over cosine, or in this case 7 over 3. Now to find the angle, we just take the inverse tangent of 7/3. So let's clear that. We need inverse tangent of 7 divided by 3, and I'm going to make sure that this is in degree mode. It's in radians. Let's switch it over to degrees. And the answer is 66.801. 66.8 because it says to the nearest tenth of a degree. Let's do the same thing with 4, negative 5. We have 1, 2, 3, 4, 1, 2, 3, 4, 5. So the x is 4, the y is negative 5. So we're looking for the inverse tangent of negative 5 over 4. Y over x, sine over cosine, opposite over adjacent. It all means the same thing. So the tangent of theta equals negative 5/4. So theta is equal to the inverse tangent of negative 5 fourths. Inverse tangent of negative 5 divided by 4. And it gives us a negative angle. So theta is equal to negative 51.3 degrees, but that's going in the negative direction, of course, and we want ours to be going in the positive direction. So it's 360 degrees, but 51 degrees short of 360. So I can take 360 and minus 51.3 degrees. So the answer we're looking for is 308.7 degrees.